Hi everyone, welcome to our webinar. The title of webinar is 3D Slope Stability Analysis using Slide3 and RSPile. Um, my name is Sina Javankhoshdel. I am the product manager of Slide3 Software. Today I have here with me Dr. Terence Ma, who is the senior engine developer of Slide3 and who's the person responsible for developing this feature in the Slide3 software. So if you have any question, he's the best person that can answer your questions. So we are Rock Science. We are the world leader in developing 2D and 3D software packages for civil, mining, and geotechnical engineers. For over 25 years, we have built geotechnical tools used by more than 10,000 users around the world. We have over 65 employees at our head office in Toronto, which you can see in the picture, the office, more than half of which they have master's and PhD degrees in engineering. In this webinar, I'll start with an introduction to Slide3 and RSPile software. Then I'll talk about 2D analysis, which is an integration between a Slide3 and RSPile, and this is the basics for the 3D stuff. And then we go to the 3D analysis, and Terence is gonna talk about it in more details. Okay, let's start with an introduction to Slide3 and RSPile, and let's see what they're doing. If you look at this picture and the area that we picked, this is a slope. That the failure of this slope would be dangerous for the cars passing the road that you can see in the picture. And we need to check the stability of this slope. So this is a typical slope stability problem. If you want to analyze it in 2D using limit equilibrium method, you can use a Slide2 software, which is our 2D slope stability tool. And if you want to analyze it in more depth in 3D, you can use our 3D limit equilibrium software, which is Slide3. So if you look at the picture here, basically we drew the slope, and you can make the same model in the Slide2 software as a 2D model. And a Slide2 shows you the most critical slip surface with its corresponding factor of safety, as you can see in the picture on the right. So basically, a Slide2 is telling us that the area surrounded in red is most likely to fall off the slope and into the road. The factor of safety that the software is showing is 0.93. The definition for the factor of safety is resisting forces dividing by the driving forces. And since it is 0.93 and it's less than 1, it means that our driving forces for this specific example are larger than the resisting forces, so the slope will fail. If you want to model this in 3D, you have a couple of options. One is if you have enough information, you have the surfaces, topographic surfaces for the area, you can make real 3D model in the Slide3 software. So the geometry capabilities that this software has, it's like one of the best in the field. You have other options as well. You can import the 2D model and extrude it to make a 3D model. In a Slide3, similar to the 2D limit equilibrium, we balance the forces in 3-dimensional. And you can look at the 3D geometry and 3D geology on the factor of safety. And for this specific example, we have the factor of safety of 1.01, which is about 10% larger than 2D. Now we know that slopes are designed with the factor of safety of less than 1.5. which we saw that it was like around 1 or less than 1 in this example. So we can use supports to increase the factor of safety. Supports work in two ways. They either increase the resisting forces in the factor of safety equation, or they reduce the driving forces. For example, in this model, you can see that we use tiebacks to increase the factor of safety to 1.5. And reinforcements such as tiebacks and piles, they increase the resisting forces in the factor of safety equation. Now, if we come to RSPile software, RSPile is a standalone software that solves for pile stress and reaction. These reactions are against applied soil displacement or other loads. And the software is capable of modeling complex pile models using the load transfer curve method, which is a finite element method. The soil load transfer curves capture the nonlinear soil pile behavior by relating the soil reaction forces to the soil displacement at each depth. There are various recommended load transfer curves are available in RSPile, and you can go to the theory manual of the software and read them in more details. So what we're gonna do in this presentation and webinar, we're gonna show you how to reinforce slopes using piles and analyze them using RSPile Slide 2 and Slide 3 software. If you look at this picture, the integration between our software packages, we have other integrations as well. And this is what is unique about rock science software packages. So basically, if you look at the Slide 2 and Slide 3, any model that you have in 2D, you can take it to a Slide 3 and extrude it and make it a 3D model. On the other hand, if you have a 3D model, you can make as many sections as you want, 2D sections, and bring it to a Slide 2 and analyze them. For both of these software packages, you can integrate them with the RSPile software to do pile analysis. So basically, you do the pile analysis in the RSPile software and bring the results to a Slide 2 and a Slide 3 for the slope stability analysis. Slide 2 used to have this option for a couple of years, and recently we added this option to a Slide 3, and that's why we wanted to show you the results in this webinar. Let's start with the 2D analysis, and I'll show you what's happening in 2D, and I'll show you one example, how to set up the RSPile model, and then I'll pass the presentation to Terence. Before I continue, you're gonna see a poll on your screen that we have a couple of options here for our future Slide 3 webinars. You can pick either of them, and if the webinar that you like is not among these, you can just type it in the chat section and let us know what you want for our future Slide 3 webinars. Okay, let's continue and talk about the 2D analysis. So piles in limit equilibrium and how we handle it in Slide 2 and Slide 3. Slide 2 and Slide 3, they use limit equilibrium, which means that it solves for the balance forces in a static equilibrium. And similar to other supports, a reaction force from the pile is assumed where it is intersected by the critical slip surface. This is the basic in limit equilibrium method. So where this reaction force is coming from, so we assume a soil displacement vector to act on the pile from the critical slip surface. This displacement can have axial and lateral components, and oh, sorry, probably, yeah, it's because of the poll, you can't see my screen. So let me, yeah, it's closed now. Yeah, now you can see my screen, I think. Yes. Okay, so A soil displacement vector is assumed to act on the pile, which has axial and lateral components. Sometimes the ultimate capacity of the pile is used. Sometimes you can just assume a maximum allowable displacement. We have these two options in the Slide software. So when this displacement is applied, the pile is solved using the imposed displacement as a boundary condition. And then solution occurs for the axial and lateral components, but you have the option to pick axial only or lateral only pile analysis. The internal forces at the location of the critical slip surface they are taken as the reaction forces of the pile acting on the sliding mass. And this reaction depends on the depth of the slip surface and the angle of the critical slip surface. So if you look at this slide model, you can see that these red arrows, they are the displacement applied from the critical slip surface. And you can see that this vector, delta soil vector, which is assumed to be tangent to the critical slip surface. This vector has two components, axial and lateral component. And then we use these components to calculate the axial and lateral resultant forces from the pile, and then get a resultant force from these vertical and horizontal forces of the pile. So these are the output charts from RSPile. So we look at the sliding depth at the location that you can see with the dashed line, and the axial forces of the pile from this axial displacement that is applied to the pile is going to be the reaction of the pile against a sliding for axial forces. Also, the shear force of the pile, as you can see here, it is going to be the lateral response of the pile against sliding. So you have both axial and lateral components. And we take these values to Slide3 software for the slope stability analysis. So let's look at our first example, and I'll explain what's going to happen in this example. Basically, if you look at the right figure, we have the support type of RSPile. So you select the support, you change the type to RSPile in the Slide software. You prepare a RSPile file in advance, and then you can import it to the Slide software. When you import it, you have to match the material types in a Slide and RSPile, as you can see in the right figure. Also, you can define like out of plane spacing, you can define the soil displacement. As I mentioned, you have two options: maximum allowable displacement or the ultimate capacity, that we increase the displacement that until to the point that the pile reaches its ultimate capacity. So this is how we set up the model in a slide. So in this example, I'll show you from the beginning how to do this. So I have one initial RSPile model, and I have one initial slide model. So this is an unreinforced slide model that I want to reinforce it with pi. So let's quickly look at the slide model that we have. Basically, we have three different material types. We have different layering. So in general, we have three different material types. And you can define support types here, which, as I showed, we have the RSPile option. So if we go to the RSPile model, there are some parameters that you have to define in RSPile in advance as an initial RSPile file that you are importing to a slide. And there are some parameters that you don't have to define initially. So I'll show you these parameters here. So if we go to soil properties, you can see that the same soil types that I had in the slide, I have to define it in RSPile. So since my pile, I assume that it is axial and lateral, So for both of them, you have to define the material properties separately. So soft clay, dense sand, and medium sand, we define the material properties, matching the properties in the slide software here. So this is one thing that you need to define in advance. If I go to project setting, you can see here that I defined the axially and laterally loaded pile. So this is what I selected. You can have axially only or laterally only piles as well. The other thing that you need to define is what type of pile you want for this model. So I defined a steel pipe. So it is a pipe, and these are the diameter and the thickness of the pipe, and I assume that it is elastic. You have other options as well: plastic, reinforced concrete, pre-stressed concrete. So you have different options for your pile analysis. The next step is to define the layering that you want. So if I go to the borehole manager, you can define the layering. But the thing here is, if we go back to the slide model, I would like to define two piles. They may go to different material layers with different thickness, and we don't know the thickness in advance, and you only use one pile type for the entire analysis. You can change and have two different RSPile models, but for this example I want to use only one pile RSPile model for different pile lengths and for different locations in my slope. So I don't know the layering, and the layering is not constant. That's why you just need to define a constant layer or any layer thickness that you want here, and these values, they're gonna be read from the slide software. So it's these values that you put here, they're just placeholders. But if you want to verify the results of RSPile integration with the slide, at that point you need to define the actual thickness. So that's the other point. So I define these layerings here. So I have only 3 layers that I have in the slide model. Then you need to add the pile. Here is the pile type 1. Let's go and define this. Other parameter that you don't need to put the exact number in advance is the pile length. Because as I mentioned, I use the same RSPile file for 2 different pile lengths, and this value is going to be read again from the slide software. So I just put 21 here. And the other parameters that you don't need to put anything is loading, displacement. These are all constant. They all come from a slide software. So I just hit OK here and put my pile at the location of 0 and 0, and the pile is being added. You can right click on the pile and edit the pile and edit the information. So I'm gonna save this pile as like initial 2. Now let's go to the slide software and read this RSPile file. First of all, I'm gonna add my supports. So I'm gonna add 2 supports. You have the option to add support pattern or add individual support. Let's say it's support 1. Hit OK. The first support is gonna start from here at 71.44 and it's gonna go to 71.19. The second one is gonna be at 65, so it's gonna be 65 and 19. So you can see that the pile length is gonna be different, but the type is the same. So I go to properties, define support. For support 1, I change it to RSPile, change the type to RSPile. So here you need to add a file, or you can go directly to RSPile software and define your model. So I created a file in advance, the file that we created together, and then we go to we can see that this window pops up. It has all the materials defined in both software. I just click here to just show the ones that is being used in the slide software, and you need to match these materials in slide and RSPile. You can see if the order is different, you can change different materials from RSPile. So you match 1 to 1, hit OK. For out of plane spacing, I put 5 meters. And this is the option that I mentioned. You can define maximum allowable displacement or ultimate. The maximum allowable displacement for design is typically 25 millimeters or 1 inch. So I keep it as is and hit OK. My piles are changed, my supports are changed to RSPile supports. So both of them, they are the same. Now the only thing that I need to do is to save this file as something else and compute. When I compute the file, first RSPile starts computing, it does the pile analysis, and then a slow stability is gonna start. So I'll show you what's happening. So I hit on compute, and it's probably going to my other window here. This is the slide engine, and this is the RSPile engine. Okay, so let me see. So the pile is doing the analysis, and now it is doing the slow stability analysis. The slow stability analysis is done. Now we go to the interpret to look at the results. So if I bring the interpret to this window, so this is the result of slow stability analysis with piles as support. You can look at the reaction force from the pile as I showed you before. So these two are different reaction forces that we have from two different piles. Their length is different, the layer thickness for each of them, soil layer thickness is different, so the reaction forces are different at different elevation. And also you can look at the bolt force diagram for the piles, and you can see that it is a non-linear force diagram, in opposite to the cases that we just use one constant shear force for the piles, for micro piles. So it's a non-linear diagram coming from RSPile. So that's how a slide 2 is integrated with RSPile. And now we can talk about the 3D analysis. So this is the result that I showed you, and let's go to the 3D analysis. I'll pass the presentation to Terence, and he's gonna share a lot of interesting information about Slide 3 and RSPile with you guys.
All right, hello everyone. Thank you, Sina, for the introduction. My name is Terence, and I'm going to be showcasing our new Slide 3 feature where we can use RSPile in 3D limit equilibrium analysis as well. So just before we go to some of the examples, I did want to talk about a little bit of the theory behind the 3D integration of RSPile. So the first thing is that now in 3 dimensions, we have 2 lateral components of the soil displacements that are applied to the major and minor axes of the pile. And then also we still have the axial components. Additionally, in 3D, you would also have to fully define the orientation of the pile in 3 dimensions. So the direction of the pile into the ground can be specified as either a vector or a trend and a plunge. And then you would also have to, once you have the direction of the pile, you would have to rotate the pile about its own axis as well. And I'll show you how to do it in a bit, but we would be using the add support feature, just like we would for any other types of anchors and supports. And also, before I go on, just a reminder for everyone to, if you have any questions, feel free to type them in the chats. And we'll get to them at the end of the presentation, hopefully. And if we don't get to them, then we'll respond later on via email. So just going over the dialog that we currently have in the program, this can be accessed through the define supports option, and it's very similar to what you would see in slide 2. We have the option of the active versus passive approach, where we would put the force of the anchor on either the numerator or the denominator of the factor of safety equation. And then again, we still have the maximum ultimate soil displacement and as well the ground slope. You can either calculate the ground slope automatically from slide 3 or specify the ground slope in RSPile, and it affects the result by a little bit in some cases. So I'm going to go over 2 examples. The first one is a extrusion of the model that Sina had just presented to us. So we're simply going to extrude this into 3D, and I'm just going to bring us to the program and show us how to do it. Okay, so here we have a new instance of slide 3 opened on my computer, and then I'm just going to import the project that Sina had used. So we'll select this file and we want to extrude it. So if you have more than one scenario in the slide 2 file, you can choose which scenario you want to import. In this case, we only have one, so I'll hit OK. And then it's going to ask you for an extrusion depth. You can enter whatever you want. And you want to take a note of some of these notes here. Sometimes some of the features in slide 2 can't necessarily be moved into slide 3, or you would have to just change them a little bit because the 2D and 3D analysis are fundamentally different. So hit OK. And then here we have the extruded model. You'll notice that if I click on the visibility icons here, you'll be able to see the piles that have been successfully imported into the model as well. And I'm just going to go to the define support dialog, and we're just going to make sure that the pile materials are matched as they were in slide 2. And so you can see here that by importing the RSPile file, we can match the materials into slide 3 again. And then you can click this checkbox as well to get rid of the unused materials. So we'll hit OK. We'll leave everything the same as before. So we'll calculate the ground slope automatically from slide 3 geometry. And then also the soil displacement, we'll just leave it as 25 millimeters or 1 inch. And then before we hit compute, we always want to check our surface options. So in this case, we're just going to use the standard search method of ellipsoid surfaces with cuckoo search. And then we will optimize the surfaces to get the minimum factor of safety that we can. And then normally I would hit compute here, but just to save time, slide 3 does typically take a little bit longer than slide 2. So we pre-computed the results. I'm just going to show them to us here. So this is what the results look like after I computed it. As you can see, the actual critical slip surface here is very similar to the one that Sina presented, with the slip surface going through the sort of the weak orange layer here. And I can actually show, again, we can show the results of the bolt forces by clicking on this button. And then you can see here, we have arrows indicating the direction of the resultants, as well as the magnitude of the forces of the bolts onto the slip surface. It's a little bit cluttered, so what we can do is we can go into the view options or the display options, and then change the number of decimals that are used for the forces. So we'll just use auto here. And then you can also change the colors of the bolt forces. So right now it's coloring them based on the type of pile, but we can change the color here, or we can change the force value. So if we click force value, it'll actually color the forces based on their magnitudes. So that should make it a little bit easier to visualize. And so for my next exercise, we actually want to verify one of these results of the bolts. And so I think what we'll do is we'll verify the result of this pile in the middle here. It's going to be in the middle of the model in the downslope pile. Just show the pile here real quick. So it's going to be this one with magnitude of 761 kilonewtons. And we're going to verify it by actually going into RSPile itself and creating a model that gives us the same result. So let me just go back to the presentation. There's a few things we want to note here about the pile and its intersection with the slip surface. So first of all, we want to confirm the sliding direction, and because that's actually the direction of the soil displacement that's going to be applied to the pile. And then we have the ground slope of 34 degrees, and that's in a direction. So the ground slope in 3D is actually a vector. It's going to be a dip of 34 degrees at a trend of 270, or in the negative x direction. And then the pile is located 12.6 meters below ground. You can actually find this from the column viewer in slide 3. And then also the base of the column that the pile intersects has an angle of 4 degrees. We also need to know the thicknesses of the soil layers that are intersected by the pile. So in this case, they're here. And then what we're going to do is we're simply going to partition the 25 millimeter soil displacement into the axial and lateral components, as shown here. And then we're going to enter that into RSPile. So let's go into RSPile. Okay, so here I've kind of already gone ahead and I've entered the soil layers in. You would do that by going into the borehole editor, and then you can change the thicknesses. We've also defined the materials from this dialog. So all of these materials, you have to define a few extra materials, material parameters for the RSPile analysis itself. But these are the same that we used in the other model, the model that we used in the slide 3 model. And then the last thing here is I wanted to show that I've entered a ground slope of 34 degrees in the negative x direction, or a trend of 270 degrees. And then for the actual soil displacements, I went in and I added a displacement profile. So here we went from depth of 0 to 12.6 meters. We have the soil displacement vector of 25 millimeters partitioned into the x and z directions. And then past that, we assume that the pile or the soil does not move. So past that, we have 0 displacements for the soil. Okay, so hit that, and then you would compute it, and then basically you would just look at the shear force diagrams and the axial force diagrams. And so in this case, we have a maximum shear force at the location of the sliding depth of 561 kilonewtons, and then a shear force in the y prime direction. In this case, it's 0 because the entire soil displacement is in the x prime direction. But there will be an example after this where it's not always, it's not exactly in this direction. So then you would get a component in the y as well. And then finally, the axial force has a maximum of 476 kilonewtons at the location of the pile, where it intersects the slip surface. So we'll take this information and we'll go back And basically, we can use Pythagorean theorem to calculate the resultants, and we get a result of 736. Sometimes it's going to be a little bit different from the result from slide 3. So in slide 3, we got 762. And this is actually due to an interpolation. So the way this works is slide 3 calls RSPile to evaluate the reaction at various sliding depths along the pile. And then it takes the results and interpolates it. So sometimes you might get a little bit of a difference, but the difference is never really big. So that's the first example. The second example that we have is actually a case study that we published. Some of the literature that we've published into the conferences. And what we did was we took a model with some contour geometry, and we imported it into slide 3. And then we used the borehole manager to specify the thicknesses of the layers at each borehole. I'm not going to go into too much detail about how this is done, but we do have a lot of tutorials in our learning section that you can visit. That you can sort of learn to import the contour geometry and use the borehole manager. And so for this example, we have a factor of safety of 1.36, and we're only concerned of the failure mode where the model slides from the top to the bottom into this sort of valley here. And we want to reinforce the slope to have a factor of safety of at least 1.5. And then these are the material properties. And so how we're going to do that is we're going to add basically a 30 by 3 array of piles covering a 700 by 100 foot area in the plan view. And these piles are going to be rectangular, just to show us how the orientation works in 3D. And then they're going to have a trend of 27 degrees from the y-axis and a plunge of 80 degrees. So that's downwards into the ground, 80 degrees. And we did this just to sort of try to align the pile's major axis of bending with the perceived direction of the sliding. And then after that, once we've oriented the pile into the ground, we're not going to rotate the pile about its own axis, so we have a rotation of 0. And then in terms of spacing, we have 40 by 24, length 78 feet for each pile. And that's pretty much it. So in terms of the pile itself, it's going to be a reinforced concrete pile. And we're only going to use the lateral reaction for this example, just to be conservative. And then again, in RSPile itself, we have to specify some additional soil parameters, such as the initial stiffness and the initial subgrade modulus of reaction, just so that it can compute the finite element analysis. So spoilers, I just showed the results, but the first thing I'm going to do is I'm going to go into our pile model just to show what's been done. Sina has gracefully shown us how to enter all this information in. But basically, I wanted to show that we have set the laterally loaded analysis type only, so there's not going to be any axial component considered in this analysis. And then what else do we have here? I guess the soil properties, we've defined some values here for the soils. Like the initial stiffness here. You want to make sure that your unit weights and your friction angles, things like that, match those from slide. But these have been predefined, so that's good. And then in terms of the pile section, you can kind of see it here already, but we went into the section properties and then we designed the location of the rebar. So you can kind of get rid of these position labels for clarity, but you can change the layout of these rebar spacings and things like that. You can set it to radial or rectangle, or in this case, we have a custom layout. And so we've already done that, but anyway, we'll take this model and then we'll import it into the slide 3 the slide 3 slope. Okay. So here we've predefined, we've already made the contours, we've gone through the borehole manager. We've also defined some slope limits here. If you look at our tutorial section, there's a tutorial on defining slope limits. Basically what these do is it forces it so that any slip surface that gets generated has to go through both of these search limits. So in this way, we are, as I mentioned earlier, we're only consider about the failure mode of sliding from the top of the model into the valley. So we've entered these slope limits in as intersects. And then what I'm going to do now is I'm going to define the pile property through define supports. And then we're going to change this into an RSPile model. Select RSPile, choose the file that we want. So in this case, it would be the rectangular pile that we just showed. And then it's going to ask me to match the materials. So we're just going to match the ones that we've defined. And then we'll hit OK. We'll leave everything else the same. So soil displacement is going to be 1 inch. And then we'll calculate the ground slope automatically from slide 3. So we'll hit OK. Now we can actually add the array of piles into the model. So we'll go into support, add supports. And then it's going to ask for a few things here. So this rectangle here, it shows the sort of like the plan location of where the piles will go. So we're going to change this to 700 feet by 100 feet. And then we're going to go into the properties, change the bolt length to 78 feet. And then the spacing is going to be 24 by 40, as we mentioned. And you can see the UI will automatically update with how many piles there will be. And then in terms of the orientation, we specified that we want the pile to be trend and plunge of 27 degrees and 80 degrees. And then we're not going to rotate it about its own axis, so we'll leave this as 0. So we'll hit apply. And then you can change some of these settings here, so you can project it either on the terrain or the actual volume. We're going to leave these as is. And then in terms of location, I need to actually move this to where I want it to go. You can either use the move pattern here, you can rotate it, but I already have the coordinates set up, so I'm just going to enter them. And then we want to rotate it at an angle of 153, and as you can see, it's exactly where I want it to be. So I'll hit OK, and that creates all of the piles into the model. And as you can see, it actually shows the major and minor axes of the pile as well. And the piles have been inclined 80 degrees plunge. So that's actually all we need to do. Obviously, you can specify search settings and define slope limits however you want. We're just going to use the defaults. And then we'll save this file and compute it. I'll just save it somewhere. And again, we've pre-computed the model just for the sake of time. And so I'll just bring up the results. And you can see here that we have factor safety 1.67. Just gonna hide a few things in here to make it clearer. So we'll hide the water table, we'll hide all these boreholes, select them all and hit the visible icon. So that should be a little bit clearer. There's a few things we can do with these results. So again, we can show the bolt column forces. You can see that they all touch the slip surface where the piles are. I'm going to also probably show where these piles are. And there is an option to only show the piles where they intersect the slip surface. You can go here and click on show intersecting bolts. I'm going to go ahead and change, sorry, I'm going to go into view options. I'm going to change the number of decimals. And again, color them by force, just to make it a little bit clearer. And then another thing we can do here is we can show all of the surfaces that were searched during the search. So I clicked on this Show All Surfaces button here, and it's able to show us that the search was able to search the entire model, and that all of these surfaces conform to the search limits, these two boxes that I've defined as well. So that's nice. And then finally, there's also the surface safety map. If you want a sort of a clearer picture of where the problem areas are in your model. And so this red here shows that the red is basically where the lowest factor of safety exists in the model. And then the final thing I want to mention is you could also add some 2D sections to this model. I'm not going to do it. We've done a few other webinars where we did, but just for the interest of time, that's something that we'll probably cover on a different day. And that pretty much concludes the example here. So as you can see, we modified this this model to have factor safety from 1.36 up to 1.67 using the RSPile feature. And just a few concluding remarks here before we go into questions. And that's essentially pile analysis, as we've demonstrated today, is in slope stability, it's a coupled procedure. So you would require the calculation of a reaction force of the pile, which requires some form of finite element analysis. And then using that result into the limit equilibrium formulation requires a lot of iteration as well. And so this can only be done, as far as we know, in combination with Slide 2 and RSPile or Slide 3 and RSPile in order to do this coupled pile analysis. And so if you want to try it yourself, you can visit our learning section in the website of in both Slide 2 and Slide 3, we have some tutorials that you can go through. And just a quick announcement that we do have another webinar coming up titled Practical Aspects of Numerical Modeling for Rock Masses Using Rock Science Software. So that will be on March 1st. Please sign up. We look forward to seeing you again. And that's pretty much it. So I will pass it back to Sina to begin the question section of the webinar.
Thanks, Terence. So actually, I'm gonna pull up the polls one more time. That if you haven't voted yet, please select an option, or if it's not on this list, please type down on the chat section. There are a lot of questions, and I think most of them have been answered but by our team. So probably I've seen your question being answered in the chats and QA section. There are a couple of points based on these questions that I wanted to make. Please feel free to ask your questions. We have a few minutes and we can answer questions. But so far, what I've seen, there were questions about Slide 3 and Slide 2 results comparison. As I mentioned, in general, Slide 3 results are a bit larger. The 3D models, they have larger factor of safety compared to 2D. But in terms of comparison, we have the option in Slide 3 to take 2D sections and run them using the Slide 2 engine in the Slide 3 software and look at the 2D results and compare them with the 3D results. So this option is available, and you can try it for different models. We have a couple of tutorials doing that. There were a couple of questions regarding the soil displacement and strain of the soil. Slide 2 and Slide 3, they are limit equilibrium software packages. So basically, they just show you the factor of safety and forces and stresses. They don't deal with stress and strain and displacement. So to look at the displacement for the pile analysis, you can go to the RS2 and RS3 software, which are our 2D and 3D finite element method software packages. There were a couple of questions regarding, I'm trying to summarize the question. There were a couple of questions regarding a slide 2 and a slide 3 comparison in terms of material properties. So in the next update of the slide 3, we are trying to unify slide 2 and slide 3 options, material properties, project setting options, so that a user is able to take any 2D model from 2D section from a slide 3 to a slide 2 and match everything, search methods. So we are trying to do that, and you're gonna see it in the next update of the slide 3. So let's see if there is any other question that I haven't responded. There were a couple of questions about the slope limits. So basically in 2D, you can define different slope limits to focus the search on a specific region, or define two sets of slope limits. One is entry point and one is exit point. In 3D, we have more options. You can specify regions, volumes, surfaces to focus the search on a specific region, or intersect the tip surfaces, or even specify a region that you don't want the software search in that region. So it has a lot more options in 3D, and you can use those options as well. So Terence, it seems that there is one question that you want to answer. Please go ahead.
Yeah, there were a few questions about the, I guess, the effect of the lateral soil resistance above the slip plane. And so the assumption that we've made here is that all of the soil above the slip plane displaces by a uniform amount. And the vector above the slip plane is the same for all points of soil above that.
Okay, let's see. To create 3D analysis first, we have to make a 2D model in a slide 2? No. You don't have to make a 2D model. As I mentioned, there are different ways of creating 3D model. If you have a topographic surface, if you have boreholes from the field, you can directly create an actual 3D model in the Slide 3 software, because there are some software packages, they just bring 2D and extrude them and say, okay, it's a 3D model. Extrusion is not 100% 3D. You can change the boundary conditions for the extruded model, but the value is when you bring the actual surface, topographic surface, you bring your boreholes, yeah, and you create a real 3D model. All these are possible in a slide 3, and actually the other thing that I have to mention is a slide 3 and RS3, they mention the same 3D geometry creation. So if you want to look at the finite element results, you can directly import a slide 3 to RS3 software and do the 3D finite element analysis. So the geometry is real 3D geometry in both software. There were a couple of questions about seismic forces. We tried to answer the questions relevant to RSPile. You can do pseudo-static analysis in a slide 2 and a slide 3. In a slide 2, we have Newmark displacement based seismic analysis as well. So yes, you can define the side. You can do pseudo-static, but if you want to do like seismic response of the mines and these kind of options, these are available in RS2 and RS3. So that's the answer to that question. There were a couple of questions regarding the material models in RS2 and RS3. I think we answered them in those webinars. Let me see what else. Go ahead.
There were also a couple of questions about, I guess, like the failure modes in the soil of the RSPile. So there is a little bit of theory on the section of our websites that explains the different type of failure modes, but essentially all of the modes are being considered in the pile analysis. So in some cases, the soil can rise up in sort of like a conical wedge failure, and then there's also, I guess, maybe like a more deep shear failure as well that's also considered. So all of that information is available in our help section.
Okay, let me see if there is. There is a very interesting question. How can we find a slide surface if more than two is we have more than two slip surfaces in one area? We recently developed a unique method, a unique feature in Slide 2 and Slide 3. It is called multimodal optimization, which basically, instead of having just one critical slip surface, you can have multiple that the factors of safety are close. So it's available in both Slide 2 and Slide 3. You can go to our website and tutorial section of Slide 2 and Slide 3 to look at this feature. This is a unique feature to Slide 2 and Slide 3 in all the limited equilibrium software packages available in the field. So give it a try. It gives you interesting results for the models that you already look at just one critical slip surface.
There was another question about essentially transferring the piles from Slide 3 into Slide 2. It's not always possible because we would have to sort of project the pile if we were to do it. So if you do make a section from Slide 3 into Slide 2, you would currently still have to define the pile again in Slide 2. But at least you can still use the same pile file.
Okay, there was a question about back analysis in Slide 2 and Slide 3. Again, this is not very relevant to this webinar. Actually, we put it in the poll for the future webinars, but basically you have the option to do stats and back analysis and in the Slide 2 we have the sensitivity analysis option as well. So yes, both of Slide 2 and Slide 3 they have this option. About the manual, a couple of people asked about the manuals. Everything, our manual is available on Rock Science's website for each software in the learning section. You can look at the theory manual, you can look at the tutorials. Anything else? No, I don't see any other questions. So we are right on time. It's 2 p.m. Eastern time. Thanks everyone for attending this webinar. I think the video will be available on our YouTube channel in future. And have a wonderful day and night. Depends on where you are. Thank you.